Okay, so we start now. We're not going to wait anymore. So today we will enter the next part, the next topic, gravitation. Okay, so when talking about gravitation, first we introduce the concept of field. Okay, gravitational field. Now you see, many years ago, people were unable to make sense of what is happening in the universe. When they observe the planetary movement, some planets, they attract to each other, but they are very far away. They are very far away, but still they are able to attract each other. And then when they observe, right, some planets can move around another, some planets move further out from each other. So they start to wonder, right, what causes all this motion of the planets? Okay, how do they explain the planetary motion? Okay, so then they come out. They also, at the same time, they also ask themselves, how does the planets attract one another if they are very far away? Because there's no contact, right? First planet is very distant away, so there's no contact, so there's no forces acting on these two things. But how they are able to move towards each other? Then they started to come up with the concept of field force. Okay, a field. So what is first is we want to understand what is a field force. Okay, so field force is like a force created due to an object being in the presence of the field, being inside a field. Okay, and the field is invisible, we cannot see it, just like the gravitational field of the Earth. Okay, but you see, the Earth attracts everything move around it, like satellites and moon. Okay, and the sun attracts all 8 planets. The field of the sun is very huge, is very far and vast, until that it can attract all other objects around it, not only the 8 planets, also the intergalactic planetary or rocks or asteroids or something like that. Okay, so the field extends very far away. So something that is at very far still can experience the force from this field. And the force produced by the field is, we call it gravitational force. Okay, now in gravitation, we are going to study about gravitational force and the planet movements. Okay, and then we go to all the Kepler's laws, all the satellite stuff. Okay, now first I understand the field. So the field is like a spider web. Okay, think of it like a spider. So you see the spider, but you don't see the spider web. Okay, it's invisible. When an insect gets caught up by the spider web, okay, the spider knows who is sending the information to the spider. The spider web is sending the information to the spider. So the spider knows when an insect is stuck there. Okay, so what happened is that the spider will then manipulate the web, and it will pull the insect towards it. Okay, so same as the concept for gravity. All planets, anything that has mass, has a field around it. And that field has a characteristics that measures how strong is the field. We call it the intensity of the field. Okay, the intensity of the field. So intensity of the field is, it talks about how much force acting per unit mass. Okay, so here I have a mass, and this is the gravitational field. And if you have a substance placed inside the field, say this is 2 kg, okay, so it is inside a field, so it will experience a gravitational force, so it will be being pulled to the mass. But what is the intensity of this gravitational field? It is measured in how much force is acting, or how much force is pulling the 2 kg towards it, okay, per unit mass, meaning that n/kg. Okay, how much Newton is pulling per 1 kilogram. So for the Earth, we are already familiar with this value is G equals to 10, right? So that is gravitational field strength. Okay, so gravitational field strength is the intensity of the gravitational field. Now, here we are going to look at more detail. Will this G change or does it remain constant? Is it the same everywhere in the gravitational field? Because you think about the gravitational field is very, very huge, right? So how about if I'm very, very far away? Is this still going to be 10 or is it different? Okay, all of this we are going to look at it. Now, first is understand the laws of gravitation. There's this, we call it the universal law of gravitation. Why do we call it universal? Because it can be applied to all stuff that you see around you. Okay, planetary motion or all objects in the earth, everything. That's why we give it a term universal. Okay, so the Newton's law of universal gravitation, he says that considering 2-point masses, okay, 2-point masses, m1, m2, separated by a distance r. I'll call it r. Okay, he discovered that the force of attraction between these two masses is proportional to the product of the two masses. Product means the times, okay? The m1 times m2, it is proportional to the product, meaning that if there's an increase in any of the two physical quantity, any of the two masses, it will cause an increase in the attraction force. Okay, now he also said that the further the distance, the weaker the gravitational force. Now, in fact, he says that the force is inversely proportional to the square of the radius, to the square of the distance. Okay, so it's not just r, it's r square. So what is the difference? Difference is that if the r is double, then the decrease in the force will be 1/4. I repeat, you have r square, meaning that if the distance, you double it, then the decrease in the force is not double. The decrease in the force is 1/4. So it's a further decrease. Okay, so that is the relationship between the r and the f. So this one, we call it the inverse square law. Inverse square law. Okay, now combine these two, we get an expression. Okay, so we combine f equals to m1 times m2 divided by r squared. Now, when we form an equation, we have to give it a constant. Okay, this constant is like a proportionality. G, we give it a G. It's a constant value. So what is this G? Okay, you see, this formula tells us the gravitational force experienced by the two objects. Now, I want to make something very clear here. This force, is it the same for the two objects? Yes. M1 and M2 will be pulled towards each other by the same force. Okay, by the same force. Now, if it's the same, then here's a question. Why the apple falls towards the earth and not the earth falls towards the apple if they are experiencing the same force? Okay, the question, okay, the answer lies in the mass. Okay, so why the apple falls down and not the earth falls up? Okay, it's because of the massive size of the earth. Do they experience the same gravitational force? Yes, yes, but because of the mass of the earth is so huge that it barely moves. Okay, it barely moves, so the earth falls down. I mean, the apple falls down. The earth falls down below. Okay, now, so that's the first thing. The gravitational force experienced by the two objects are the same. Okay, so here we look at what is the G. What is the G? So the G, if I rearrange this equation, I get something like this. Okay, G equals to force times r squared divided by m1 times m2. Okay, now later that the Newton, he found out that, okay, if I place two masses of 1 kg, 1 kg mass and 1 kg mass at the distance of 1 meter from each other, what he found was that the force of attraction between these two masses is equals to a constant. Okay, what does it mean by a constant? Meaning that something that does not change. Okay, 你拿这个两个1 kg， 你放1 meter from each other， 不管在这边在哪里都好，都是它会拿到同样的一个 value。That's why 我们叫它 constant。OK， 不会变的 value， 就很像你的那个pi 这样子。Okay, for circle you heard about the pi, right? With this 3.3.142 the pi. So this is also a constant. It doesn't change. Where do you get pi? What is pi? Pi is actually the ratio of the circumference divided by the diameter. Okay, if you take any circle, you calculate the length of the circumference. You take the length of this circumference, you divide by the diameter, you get 3.142. That's how you get the pi. Okay, if you take a smaller circle, you do the same thing. You measure the circumference, you divide it by diameter, you still get 3.142. You increase the size of a circle, still you get 3.142. You take the circle as big as the earth, still you get 3.142. Why like this? So this one is like a fixed number, right? It doesn't change regardless of your circle. Okay, so this one we will say it as a constant. So that is the meaning of constant. Okay, a constant is something that never changes. It has been proven true by nature. Okay, so it's the same for the gravitational constant. So the Newton, he found that when you place 2 kg, 1 kg, 1 kg, 1 meter apart, then the gravitational force equals to a numerical value is 6.67 times 10 power of negative 11. Yes, it's very, very small, negative 11, right? Okay, so this is the value. Now, you see, the gravitational constant is equals to 6.67 times 10 pi minus 11. What is the unit of the gravitational constant? Okay, we can derive it, right? Using your mathematical skill. Okay, we change this. Force is equals to what? Newton. R is meter square. This is kg. So you get Newton meter square kg minus 2. That is the unit for gravitational constant. Okay. If you take 1 kg, okay, this one 1 kg. So G equals to F times 1 meter square divided by 1 kg times 1 kg. Then you get G is equals to the force. Okay, so since G is a constant, 6.67, so meaning that the force is 6.67 times 10 minus 11 Newton. This is the force when 1 kg apart of 1 meter. Okay, so this is what he found. And he then called this a constant, and he give it a name, is the gravitational constant, and it's inside his equation here. Okay, now, so this gravitational constant does not affected by the medium. The medium, for example, regardless of where it is, you can place these two objects in space, okay, or in inside Earth or on Jupiter, anywhere, irrespective of the medium, okay, regardless of the medium, it does not affect the G. So it becomes something that is universal, okay, something that is always true. Okay, so again, just recap again. What is the gravitational constant? Is it a force? Is the gravitational constant a force? It is not a force. Okay, be very clear that force is force. Gravitational constant is a constant. You see the unit, then you know it is not a force. Okay, gravitational constant is just information. It tells you when you do this, when you do that, it gives you this amount of force. Okay, it tells you when you bring 1 kg and 1 kg, place 1 meter, you get this amount of force. This is information, but it is not the force itself. Okay. All right. So that is gravitational constant. So Newton, he assumed this theory to be point masses. Why? Why he wanted to assume it to be point masses? Because he was not sure. He was not sure, is this formula correct for big bodies? Like if you have a big size body that is placed side by side like this, placed side by side. He was not sure that for big bodies, is the force going to be the same? Okay, so he assumed that in this theory that we are dealing with point masses. Okay, we're dealing with point masses. So if the question asks you, what is the assumption made during the formulation of this formula, then you know is point masses. Okay, point masses. Okay, so that's why this theory is actually the basic, it's just a basic law. Okay, it's just a basic law, because there are many things that Newton still wasn't sure about this one, right? Okay, so F equals to gmm over r squared. This is the formula, and F is the gravitational force. Okay, where does this come from? It's come from where? Come from the field, right? Just now we talked about the field. Field, not anything that we cannot, it's something that we cannot see, but it is there and it's exerting an influence, okay, that we cannot see, okay? All right, so properties of this force. There's some properties that worth mentioning. Okay, properties of the gravitational force. I'll call it G force. Okay, first is it is always an attraction. Okay, it's never repulsion. Okay, it's always a attraction, no repulsion. And then it is regardless of the medium. Regardless of medium. And number 3 is it is a long range force. Stars that are very distant apart, they still experience the same force. So it's a long range force. Galaxies, they can attract another galaxies. That is like millions, billions of light years away. Okay, still they can experience this gravitational force. Okay, now since force is a vector, right? So we have to be careful with the direction also. How do we label the direction of gravitational force? Here we got two masses, m1, m2, separated by the distance. So if I want to label the gravitational forces, then the gravitational forces pulling m1 is going to be towards m2. So I draw an arrow here, like this. And the gravitational force pulling m2 will be towards m1. So I label like this, okay? This F1 and F2. Are they equal? Yes, they are equal. F1 equals to F2. Okay, which mass will move towards each other? Another. Which one will move towards another? That depends on the mass. Okay, so if you already calculated the F, then you can find out the acceleration because you know the mass what. Okay, so you can take F from the previous lesson. We talk about F equals to ma, right? The force will cause acceleration. Okay, so you take a force divided by m, you get the acceleration. Okay, so you take the force divided by m1, you get the acceleration of mass number 1. You take the force divided by m2, you get the acceleration of mass number 2. Then you will know which one accelerates faster, which one will fall towards each other. Which one will fall towards the other one. Okay, in the case of objects on the earth, object will always fall towards the earth, okay, because of the huge mass of the earth. Okay, now if you look at the concept of gravity, right, so anything that has mass will attract, right, technically speaking. So theoretically, then any body of masses are going to experience a pull by each other, meaning that if you stand beside your friend, then both of you will be attracted. Okay, you can actually calculate this, how much you guys are being attracted. Okay, let's go to the next page. Say you stand like this. Okay, you stand 1 meter. from a friend. Okay, let's say you're 50 kg and your friend is 60 kg. Force equals to GMM over R square. Okay, so force equals to 6.67 minus 11, 50 times 60 divided by 1 meter square. Then you get the answer 2 times 10 power of minus 7 Newton. This becomes very, very small. So small that it is negligible. We don't count it, we neglect it. Okay, so there's a force attracting you both, but the force is very, very small, so you don't slam into each other. Okay, same thing happen as if you stand near a tall mountain. You will experience a gravitational pull by the mountain. Okay, asteroid coming in towards Earth, the Earth will experience the pull by the asteroid, but because of the mass, it barely accelerate. Okay, so any two masses will pull each other. But if you look at all the objects, attraction between objects on the Earth, they are very, very small compared to the Earth, relative on the Earth. So all the attraction on the Earth is being neglected. Okay, we only look at the Earth. Okay, any attraction between one object and another on the Earth is being cancelled by the Earth gravitational field. Okay, because it's so small that relative to the Earth that it doesn't make any significant effect. Okay. Now, next one is we look at the acceleration due to gravity. So we already talked about the gravitational force. Okay. So here we look at second one, acceleration due to gravity. Okay, let me type this out. Okay, so far we said that the force experienced by an object would be equals to G m1, m2 divided by r squared, right? And you only experience this one if you're in the field. Okay, consider an object at the surface of the Earth. Okay, so we have an object here. So it is inside the gravitational field. So it will experience a gravitational force downward. And we know that this force is equals to the mg, right? Mg. Okay, now, if this force is the net force, mind the word net force. What is the net force? Again, net force is anything that with no obstruction. Okay, you add up all the forces acting on it. This is the final forces. This is the net effect. We call it the net force. Okay, so if it's falling under a net force with no obstruction, then it will be accelerating downward with an acceleration A. Okay, now considering the position of this object on the surface of the Earth. Okay, this is Earth. Take the radius of the Earth as 6,400 km. Okay, 6,400 km. Now, assuming that all the masses of the Earth comes from the center, okay? Remember, point mass, right? So assuming that all the masses come from the center, then the object at some altitude here, this altitude, let's say is 10 km. Okay, 10 km above the ground. Okay, now here I can say, I can write an expression that says that the force attracting the mass downwards, F equals to mg, is the same as this one, right? Gmm over r squared. So I can write it as mg equals to gmm over r squared. Now you have to be careful with the m. Here I got 2m. Which one is the m of the Earth? Which one is the m of the object? Okay. Here I change this. This is ME for the Earth and MO for the object. Okay. MO. Right. So F equals to mg. This M is MO. This is MO. And this GMM, one is ME, one is MO. Okay. From here, cancels off the M. So I get G equals to GME over R squared. Okay, what is this R here? This R is the distance between the two masses, right? Distance between the two masses. So for the Earth, we count from the center. Remember, we count from where? From the center, not the surface, from the center. So the center of the Earth to the center of the object. Okay, by right, it should be 6400 plus 10 km, right? So it would become 6410. That's the distance between them. But because the 10 km is so small, compared to the 6,400, it is so small to give any significant effect. So we will not count it. We would just assume that the object is at the surface, which is 6400. I repeat, because the altitude is very, very small, 10 km, if you compare to 6,400, is nothing. It's nothing. So I don't need to count it. Okay, I don't need to count it. I will just assume that this is at the surface. Okay, so the R, I would just take the radius of the Earth, 6400. Okay, so for this one, I would write my formula as G equals to GME divided by the radius of the Earth. We use capital R square. Okay, capital R square. So even though the altitude is like 100, 200, still it won't make much difference. Unless you're talking about like 5,000 satellites. Okay, like satellites moving around the Earth. They are at very, very high altitude, 5,000, 2,000, okay? Very, very high. That will make an effect. That will change the G. Okay, that will affect the value of G. But if you're talking about within 100 km, they are all, we just assume they are all at the surface of the Earth. Okay, so the G, this one, the G is, this one is at the surface, right? At the surface. So I can call this GS, G at the surface. What is the G again? You're already familiar with this one. This is the gravitational acceleration. Because this acceleration is caused by the gravity, so we call it acceleration due to gravity. Okay, so G. Now back to the questions that I asked earlier. Is the G same or is it changing? The answer is it is changing. It changes. It's not the same. Okay, but in the previous calculation, we always use the same value, 9.81 or 10, right? Because why? Because we are assuming all calculation is done at the surface. Okay, at the surface. Even though you are at 9 km, still we will say you are at the surface. So we will still use 10 for the G. Now you are in gravitation. You need to calculate satellite and stuff, the planets. So you cannot use the same G. It has to change. Okay, how do we get this number G? So you can use this equation, GS, you take the gravitational constant, you times by the mass of the Earth, 5.97 times 10 power of 24 kg, very big number, divided by the radius of the Earth, 6400 km times 10 power of 3, change to meter. You get approximately 9.81 and meter per second square. There are many, many ways to calculate the G. This is one way, or you can do the kinematic. You drop an object, you calculate U equals to 0, What is the distance fall? 10 meter. What is the final velocity? Or you can calculate the time. Then you can use the S equals to U plus AT. Sorry, V equals to U plus AT. The kinematic equation. That one also you can calculate the G. There are many, many ways. Regardless of what method you use, you will come to the same conclusion, 9.81 at the surface. Okay, now how does the G affect our life? Why is this G important? Why is this G important? This G is the same G as this one, guys. Mg, F equals to mg is the same G. Okay, so the G, if you look at F equals to mg, which gives our weight equals to mg, how does the gravitational field strength affect our life? If the gravitational field strength is half, okay, what is your weight if this is reduced to half? Okay, we can do a bit of mathematical calculation. This is your weight at normal G. If it's half, then your weight, I do like weight dash, your new weight, okay, your new weight would be equals to mass G half, okay, and then W equals to half mg, and you substitute this one back inside here, you get W dash equals to half W. What does this tell you? Your new weight is going to be half of your original weight. Okay, so if the gravitational field strength is reduced to half, then your weight also reduced to half. On Mars, the gravitational field strength is almost half of the Earth. So if you go to Mars, here you weigh 600 Newton. You go to Mars, you are 300 Newton. So it's like here you are 60 kg. On Mars, you are 30 kg. But this cannot be because mass does not change, right? This one I just give you just a perspective, okay? So it's actually the weight that is changing. So 600 Newton, you go to Mars, it's 300 Newton. Your mass will still be 60 kg. It cannot change. Okay, so that is how much it reduces. So you feel lighter. You feel lighter there. On the moon, it's like 1/5. If I'm not mistaken, I think it's 1/5 or 1/6. Okay, so your weight will also be 1/6 of your original weight. Okay, I'm going to create a new meeting and we continue there.